last time we did first order Boolean average, we had data, and using the data, we ended up estimating the value of theta 1. Theta 1 ended up to be 0.507 something. One of the equations resulted in imaginary numbers. We shouldn't take that approach because that's probably going to give us imaginary numbers. But if you put in the imaginary values, of course, it will satisfy the equation. We will talk about using imaginary numbers later on when we get to autoregressive points. The idea here is the same. I went over first order difference equation, second order difference equation, third generalized it to E. I'm going to do the same thing. We did MA1, we will do MA2, we will do MA3, generalize it to MAQ. By the time we get to MAQ, you will recognize the pattern. I'm sure with MA3, you'd understand the pattern. So if I asked you, well, what should the series look like for MA2? What would it look like? Take a look at your notes. Look at MA1 and tell me what MA2 would look like.
Would it be theta 2 epsilon t minus 2 plus theta 1 epsilon t minus 1 plus epsilon t?
That is correct. So we will have yt equals mu plus theta 1 epsilon t minus 1 plus theta 2 epsilon t minus 2 plus epsilon t.
I've got it.
Well, yeah, that is the last error part. We of course subtract the mean. If I subtract the mean out, let's say it's equivalent to saying mean mu is 0. And the polynomial on that side is.
Wait, does that mean that in the MA1 model, technically the mu is there too?
Yeah, but I kept it as 0 last time.
Okay.
So we don't move this to the other side and find the characteristic polynomial, rather we're going to make use of the Covariance function and such to determine the values of theta 1 and theta 2. Before we get into that, we would like to know if MA2 process is stationary. We can't prove strict stationarity always, so the closest we could get is weak sense stationarity. So the first condition is the expectation of yt. We will distribute and theta 1 expectation of epsilon t minus 1 plus theta 2 epsilon t minus 2 theta 3 oops epsilon t.
Not yet, but not yet.
Exactly, not yet. Now, what do we know about epsilon t? Our basic assumption is epsilon t is normally distributed, IID, mean 0, standard deviation, sigma squared. Independent, identically distributed, no correlation whatsoever. So when I take the expectation, that one's going to be 0, that one would be 0, that one would be 0, everything becomes 0.
My favorite equation.
right? Everything becomes 0. Part B, or the second condition, is to determine the covariance function yt comma yt plus h.
What does I mean again?
Independent and identically distributed. It's a way of saying that things aren't correlated and they have the same distribution. So the covariance of yt comma yt plus h is gamma h. I'll give you a second to write.
Is it true that Bill, you actually get here in dark class?
So, by the looks of it, gamma h over here seems like it depends on time t, right? But if you recall when we did LA1, it seems so hard to do this directly, but what did we do? We picked specific values of h and then apply that to see if it depended on the time. So let's start with h equals 0. If h is 0, I am finding gamma sub 0. What does gamma sub 0 equal to? It has another word.
Isn't it 1?
So gamma naught simply means the covariance of yt onto itself. Well, how does yt vary with itself? That would be the amount of variance that you have, because yt is a random variable. So if I put in 0, I mentioned last time we are only interested in terms that match up in time indices, right? So when I put h is equal to 0, those two will match up, right? That and that will not match up. That and that will not match up, right? So I will have covariance of the first two terms. Plus, when I plug in 0, that and that would match up. Yes. That and that term is not going to match up. And that and that term will not match up in the time indices. So the only thing that would match would be t minus 2 here, t minus 2 there. So covariance of theta 2, epsilon t minus 2, comma theta 2, epsilon t minus 2.
And then obviously you just have the covariance of epsilon t, comma epsilon t.
Exactly. So when I plug in 0, that becomes t, excuse me, that becomes, sorry, when I plug in 2, that would become t plus 1. T plus 1 cannot be correlated with t minus 2, t minus 1, gone. When I plug in t equals 2, I would have t epsilon t by itself, and then
Why are you talking about h equals 2? I thought we were talking about h equals 0.
oh, thank you. H equals 0, then this would become t minus 2.
Doesn't match the way.
Come again?
Doesn't match the third.
For the last one, it's not going to match, right? So let's see, I got confused here for a second. So I'm plugging in for h equals 0, and h is 0, I will get that first term. Oh, we are looking at the very last one.
Yes.
So when h is 0, you will have that. It felt like I was going in circles, which I was.
Oh, where?
Which I was.
Yeah, I was like, when did we skip one?
Yeah, when did we stop? So you have theta 1 here, theta 1 there, both of them are constants. If you pull them out, it would become
The theta 1 covariance epsilon t minus 1.
so just theta 1,
Theta 1 squared.
theta 1 squared, covariance of epsilon t minus 1, comma epsilon t minus 1. What about the next term? Theta 2 comes out, it would become theta 2 squared, covariance of epsilon t minus 2, epsilon t minus 2, and lastly we have covariance of epsilon t, comma.
Oh wait, do we get theta 1 squared and theta 2 squared because those are technically two separate terms?
Come again.
Do we end up with theta 1 squared and theta 2 squared because those two are technically separate terms?
Yes. So what is covariance of epsilon t, comma epsilon t? That's the variance of epsilon t. Same arguments that were made with respect to yt. But if I change t to t minus 1, covariance of epsilon t minus 1, epsilon t minus 1 will still be the variance of epsilon t. So theta 1 squared, variance of epsilon t minus 1, theta 2 squared, variance of epsilon t minus 2, and the last one is variance of epsilon t. Correct? Epsilon t is normally distributed, and it is identical in the sense that it have the same distribution. So all of them, for all time t's, will have sigma squared as the variance. So theta 1 squared, sigma squared, theta 2 squared, sigma squared, plus sigma squared. Yes? What do they have in common? Sigma squared, so we'll have theta 1 squared plus theta 2 squared plus 1. That is gamma. So we have shown that in part A, or point A, that the expectation is constant, it ends up being 0. If mu wasn't 0, then that expectation would simply be mu. I picked mu to be 0 because oftentimes in practice we can always subtract the mean out and proceed with a regular simple time series. So clearly gamma naught does not depend on time t. But we can't jump to conclusion yet because this is an MA2 model, so we've got to look all the way up to gamma 2. So if I set h is equal to 1, gamma 1 would be covariance of y1 or yc, comma yc plus 1. The book might use j instead of h, and it might go t minus j instead of t plus j, but an important property of gamma h is that gamma h is equal to gamma negative h. They're one and the same. Whether you go in this direction or that direction, the correlation is going to be the same. So I like using h and I like to go with the positive side. That will be covariance of theta 1 epsilon t minus 1, theta 2 epsilon t minus 2, plus epsilon t, comma, theta 1 epsilon t plus h minus 1. I can plug in the h, right? If I plug in h equals 1, 1 minus 1 would be 0, so we would get theta 1 epsilon t. When I plug in h equals 1 here, 1 minus 2, epsilon t minus 1. The last term, when I plug in 0, it's simply epsilon t.
That would be epsilon t plus 1.
Oh. Thank you, Alex. Because h is 1 now. When I was at h is equal to 0, I was thinking about h is equal to 1, and now I'm thinking backwards.
I did something.
Good. Now, as I mentioned earlier, all we care about would be the terms where the time indices match. Clearly, that and that doesn't match, but that one and that one matches. So I can write it as covariance theta 1 epsilon t minus 1, comma theta 2 epsilon t minus 1. Is that it? We looked at the first term.
No,
Obviously, this and that doesn't match up. T minus 2, t doesn't match. Doesn't match. T minus 2, t plus 1 doesn't match. T matches, right? The rest is all 0 because epsilon t minus 1 does not match, t plus 1 does not match, so that's all we have.
Wait, so why are we saying that theta matches?
Theta's a constant.
This one,
Yeah,
So,
so it matches the one without it.
t matches.
So only the t's, not the theta.
Yeah, only the t's. We have to look at the time indices. So in this case, if you look at t minus 1, t minus 1 matches the t minus 1 there. So time indices.
I might just be having a bit of a range for it, I suppose, but why is it always 0 when it doesn't match?
Because they're not related.
So the fundamental property of epsilon t is that they are not correlated. Correct? They are uncorrelated, independent and identically distributed. So whatever you measure for epsilon t at time t must have no connection to time t minus 1, t minus 2 all the way. This side, t plus 1, t plus 2 all the way, that side, right? But it can vary with itself because it's a random process. So if you pick an arbitrary time point t, as long as it is epsilon t, fine, it will be the variance. Epsilon t minus 1, epsilon t minus 1, variance. But the moment you go on either side, they all will be 0 because they are not correlated.
Okay.
Well, I've got to pull theta 1 out, then theta 2 out, so theta 1, theta 2, covariance of epsilon t minus 1, epsilon t minus 1. What about the next term? Theta 1, covariance of epsilon t, epsilon t. What is covariance of epsilon t minus 1, epsilon t minus 1? Variance of epsilon t minus 1, which we know is sigma squared. Same over there, theta 1, sigma squared, which would result in theta 1, theta 2, plus theta 1, sigma squared.
we was right like that, or can we also take out the theta 1 as well?
What do you mean? Let's keep it this way.
Okay.
Good question. I'm keeping it this way because we'll recognize the pattern when we go later.
Gotcha.
Here we look at yt, comma, yt plus 2. In other words, we're finding gamma 2. If I write the expression, I will get it's 1 epsilon t minus 1, theta 2, epsilon t minus 2, epsilon t. And when I plug in 2 there, I will get theta 1, epsilon t plus 1, 2 for h, theta 2, epsilon t, 2 for h, epsilon t plus 2. Yes? Epsilon t minus 1 is not going to match with any of those type indices, 0. Epsilon t minus 2 is not going to match with any of those time indices, 0. Epsilon t is not going to match with epsilon t plus 1, but it will match with epsilon t. The other term will be 0. So what we will have left would be epsilon t, comma, theta 2, epsilon t. And what is in common between the two terms?
The epsilon t.
Well, theta 2.
1 and theta. Well, I see what you meant. In terms of the constant, we have theta 2. I posed the question incorrectly. So what is covariance of epsilon t, comma, epsilon t?
Thickness squared.
It's the variance. So theta 2 signifies 1.
Keep thinking in terms of algebra, like when you pull out the theta 2, it'll be theta 2 covariance, like 1 over theta 2, comma, et.
It's not algebraic,
Yeah,
right?
like
Yeah, this goes back to, earlier first week, maybe second, we had expectations, and I showed the properties of expectation. But there, if you pull that 1 over theta 2 as a constant out, it will come to this here. So our covariance function is defined to be 1 plus theta 1 squared plus theta 2 squared multiplied by sigma squared. And that is when h is equal to 0. What was it? No, theta 1 plus theta 1, theta 2 multiplied by sigma squared and h is 1. Lastly, it would be theta 2 sigma squared when h is 2. For all of the values, it would be 0, and we can see the expression for individual cases of h at individual lengths does not depend on time at all. It purely depends on h. So that is our condition for White's and stationary, that the series must have constant expectation. In our case, that is 0, and the correlation function, autocorrelation function must depend only on H. Well, if the autocovariance function depends only on H, that's true for the correlation function also.
What is H supposed to be anyway? It just.
So clearly, MA2 is quite stationary, so we're perfectly fine with the computations. Rho H is the autocorrelation function. When H is equal to 0, the function is, the series is correlating with itself. So when you find an autocorrelation, sure, if it is covariance, when a series is varying with itself, the covariance becomes variance. But in this case, the series, when we say it's varying with itself, the autocorrelation would be 1, because the strength is going to be fully positive. So autocorrelation at H is 0, no matter what function, what series you look at. When H is 1, it is gamma 1 over gamma 0. Gamma 1 is theta 1 plus theta 1, theta 2. Divided by 1 plus theta 1 squared, theta 2 squared, sigma squared. What happens to the sigma squared? It'll get cancelled. So we will end up getting theta 1 plus theta 1, theta 2, divided by 1 plus theta 1 squared, theta 2 squared. Last case, it would be the same process. Gamma 2 over gamma 0 would be equal to theta 2 sigma squared divided by 1 plus theta 1 squared, theta 2 squared times sigma squared. Sigma squared will get cancelled. We will have theta 2 divided by 1 plus theta 1 squared plus theta 2 squared. That's for H equals 2. What happens for H greater than 2? 0. It will be 0.